Hello everyone. Today we're going to get into correlation and regression. So what is correlation? A correlation is when the values of one variable are somehow associated with the values of the other variable. So we're going to focus in this chapter in statistics is we're going to focus on a linear correlation. So it's basically where we're going to focus and see, do the points line up in a straight line? And if so, how close are they to this straight line? And of course, we have a few lovely formulas for how we calculate how close they are to a linear straight line pattern. And we're going to use this number, r, as our linear correlation coefficient number. And this is a number that's going to be between -1 and 1. And the closer it is to either 1 or -1, the stronger the linear correlation is. So in other words, if the points line up fairly close to a straight line, the more likely it is that the R value is going to be either really close to 1 if it has a positive slope, or -1 if it has a negative slope. So what we don't want is we do not want R to be close to 0. And if it is close to 0, that basically means it has a weak or very little linear correlation. As far as calculating R, we're just going to focus on using technology rather than trying to use any of these three formulas. So just some examples from the book. We have an example of a positive correlation where R is 0.859. And you can kind of see that the points are definitely a little bit far apart, but you can kind of tell that there is a pattern where the line goes up and to the right. Negative correlation example, the data points are tighter and closer together. And you can definitely see there's more of a line in that example. No correlation means that points are pretty much random, where both the x and the y values really don't have any relationship whatsoever. Now, sometimes you may have a nonlinear relationship. So basically, it means that there is some other pattern that the lines follow that is not a straight line. So, for example, in part D, it has a nonlinear relationship. And in this case, r happens to be zero point 0.3. It's definitely closer to 0, but it does follow a parabola. So in that case, that would be a better example where you'd want to use some other line rather than a straight line to approximate those values. So you'd come up with some kind of a parabola to try and explain what those values are coming from or how to predict those values. Now, one thing that I need to make sure that you're aware of is that, like other things, outliers really affect R. So we need to make sure that there are, in fact, no outliers or some extreme points that are really high or really low compared to the rest of the data points. So in this example, we just kind of look at how to plot the points into a scatter plot. And the way we're going to do this in Excel is we're just going to use the linear regression t-test sheet. So I'm going to go ahead and type these values into our Excel spreadsheet, and we'll kind of see how the scatter plot looks. So unfortunately, I don't know how to fix this bug where it wants to keep the x-axis starting at 0, 0. But you can kind of see that these are the data points here. And we have this line, which we'll talk about in the next section. But for now, just know that we do have these data points kind of scattered about. They kind of look like they follow this line here. So what we need to look at next is how to calculate R. And I actually just did all that work already by plugging those points in. And our R is actually this number right here. It's 0.873 so on, right? So I'm just going to write down the first four decimal places. So 0.8737. So that is our linear correlation coefficient R. So the question is, what does this R tell us? Is this close enough to 1 in a way where we could say that this is in fact a linear relationship between the chirps in a minute and the temperature? Well, in order to figure out whether or not it has a strong linear correlation, we need to basically conduct a hypothesis test. So this is going to use some simple random samples. We need to make sure the scatter plot does follow a linear pattern. Sometimes you can have a really big R value, but the points do not line up in a straight line. And of course, we need to make sure that there are, in fact, no outliers. So our null hypothesis is, oh no, what is this? This is rho. Rho looks like a P, except it does not have a stem on this top left there. So it's not a P, it's rho. It's the Greek letter that will represent our linear correlation for the population. So rho is the linear correlation coefficient for the population. So our null hypothesis, we're going to assume that there is little to no linear correlation between our x and our y. Our alternative, of course, is going to be one of the others. However, in this textbook, we're going to always assume that there is a linear correlation, meaning it could be positive or it could be negative. We will assume that it is always going to be two-tailed. Part of this is due to the table that we use. The table that we use has to assume that these are two-tailed. And the other reason I believe is just to try and keep this a little bit easier to understand. However, you could change the settings if you were to try and test and see if it is in fact a positive or a negative linear correlation. The test statistic formula that we're going to use is that t equals r divided by the square root of 1 minus r squared divided by n minus 2. So it does actually use the test statistic t. And our degrees of freedom is actually different from what we've seen before. It is in fact n minus 2, not n minus 1. So of course, when you saw that we got our R value from our Excel spreadsheet, you probably saw there's a bunch of other stuff in that table. And sure enough, this has our test statistic and p-value listed there as well. Now to find the critical values, there is another table that we will use. I will show you that on the next slide. And one thing to note before we move on to the next example is that unfortunately in this class, we will not be doing a confidence interval. I know some of you are very upset about that. So, looking back at this, we want to conduct our hypothesis test to determine whether or not there is, in fact, a linear correlation between the chirps in 1 minute and the temperature. So, the null hypothesis, we're assuming that there is no linear correlation, so rho equals 0. And the alternative is that rho does not equal 0, meaning there is a correlation. I should be more specific that it's no linear correlation. So the null and alternative hypothesis will always be that rho equals 0 and rho not equal to 0 for this class. Now, of course, I forgot to mention what our significance level is in the problem. I'm going to assume it's 0.05. That was my fault for not including that. Our test statistic we can get from our Excel spreadsheet. So looking at the Excel spreadsheet again, our test statistic was 4.399, and our p-value was 0.0046. Even if I had picked 0.01 as my significance level, I'm pretty sure it's clear to see that this p-value is in fact less than alpha, so we would in fact reject the null hypothesis. Now it is still important to include r, because we will need that for the critical value approach. Now for the critical value, we could technically do this in one of two ways. We can either compare the t values using the degrees of freedom of n minus 2, or what we'll actually do instead is to use the new table where we compare our r value with our critical value. And the idea is that if our r critical value is greater than the absolute value of r, because again, r could be positive or negative, then we would fail to reject the null hypothesis. If our crit is less than or equal to the absolute value of r, we would reject the null hypothesis in favor of the alternative. So in other words, our crit is going to be the number that decides whether or not our R value is large enough or a large enough negative number to decide whether or not it is in fact close enough to 1 or negative 1. Looking at our correlation coefficient R table, notice that this actually uses n and not the degrees of freedom. So again, this just means we have to be a little bit careful in what we're doing here. I believe we had 8 data points. Even though our degrees of freedom was 6, we only care about the fact that it's n equals 8. And since I said that alpha was 0.05, our critical value is 0.707. And in this case, it is actually less than 0.8737. So we would reject the null hypothesis in favor of the alternative. Of course, we already got that conclusion from our p-value, but this just confirms that we know how to do the critical value approach. We have sufficient evidence to conclude that there is a linear correlation between the number of chirps in 1 minute and the temperature. So now we're going to talk about the next concept, which is the coefficient of determination r squared. R squared is the proportion or percentage of variation in y that is explained by the linear relationship between x and y. Now, I know this doesn't necessarily make a ton of sense, especially not right now, but I can tell you that once we do an example in 10.2, I will try and explain where r squared comes from. Just know for now that r squared can basically come from squaring r, and if you square a number that's between -1 and 1, you'll always get a number that's between 0 and 1 inclusively. So of course, if it's still close to 0, that basically suggests that the regression equation, which again we'll talk about later, is not going to be very useful for making predictions. And if r squared is close to 1, that means that our regression line, or the straight line that we're essentially assuming the points are close to, will be helpful and useful for making predictions. So what the question asks is, what percentage of the variation in temperature can be explained by the number of chirps in 1 minute? So what we basically do is we look back at our Excel spreadsheet and we go and look and see what r squared is. And r squared in this case is 0.7633. In terms of percentage, this is 76.33%. So just doing one more example using a hypothesis test, we're going to look and see whether or not the data provides sufficient evidence to conclude that the age and price of Corvettes are negatively linearly correlated. Now, again, we're just going to assume that we're looking to see if they are in fact linearly correlated. So ignore that negative part. To start this off, we will find the null and alternative hypothesis. Well, again, that's going to be just rho equals 0, meaning there's no linear correlation, and the alternative being that there is in fact a linear correlation. Typing the data points in, we do see that we do have a linear path, and it doesn't appear like there's any outliers. So we can go ahead and just use r, t, and our p-value and write those in for our hypothesis test. So r equals -0.9679. Our t-value is -10.887. And our p-value is 4.4 times 10 to the -6. So we basically have 5 zeros, and then we have 4. So it's a really small p-value. So we can tell that this is less than 0.05. And that means that we have strong evidence to suggest that we can support the claim that there is a linear correlation. Our critical R value, again, we have to get that from the table. And there are 10 values, or 10 pairs of data. So at 0.05, and then 10 value points. And our R crit is 0.632. And this is less than the absolute value of -0.9679. So again, that absolute value would take care of that negative. So either way, we can basically say that there is a linear correlation, or we have sufficient evidence to suggest that we have a linear correlation. So do the data provide sufficient evidence? Yes. If we think about the context of the problem, I think our results do make sense, because as the car gets older, the price should eventually go down. Now, this doesn't necessarily happen with every vehicle, but in most cases it does. So because each of these sections are short, I'm going to go ahead and jump straight into 10.2, which talks about the regression half, or how do we come up with the equation of the line. So what is the regression line? Well, this is basically the straight line that best fits the scatter plot of the data. Well, how do we determine what is the line that best fits the data points? Well, it has to satisfy what's called the least squares property, which will be explained in further detail in the next slide. So here we kind of go over some of the basic notation that we have for the population regression line and the sample statistic regression line. And we use rho versus r, or beta versus b for the different parts of the equation or the correlations. One thing to note is that in Excel, we will use a plus bx instead of b0 plus b1. Another thing to note is that we are using y hat. This is not referring to the proportion in any way. We use y hat to say that this is the line that best fits our sample data, and we hope that we can use that to predict the true line for the entire population. Now, when we do this hypothesis test or create a new line from gathering a new set of sample data, we will almost always get a different equation. And that's okay, because again, we're trying to just estimate what the true line is. And it is going to change probably both the slope and the y-intercept. Hopefully they don't change too much, but they will change every time we redo the hypothesis test with new data. So what is the least squares criterion? This is the criterion that's going to help us determine what the best line of fit is with our data set. So we have these 3 points, and I'm going to go ahead and just label the 3 points here. Now I'm using E here to represent the amount of error. So what we have is we have two different regression equations. We have 1 plus 1x, and then we have some other linear equation, y equals -1 plus 2x. Now, why pick these two equations? I mean, obviously one of them is the regression line. That's what the first one is. But the second one you might think might be a better fit because it goes through that point. So right there, it automatically goes through one of the 3 points. So it basically accurately represents 1/3 of the data set, right? So why does this equation not work? Or why does it fail this least squares criterion? Well, let's go ahead and calculate the amount of error that each graph has. And the way we do this is we make what's called the sum of squared error. Sometimes we might use SSE in short for the notation that represents sum of squared error. Well, sum of squares means that we need to sum something that's being squared. And essentially what we do is we sum up all of the amount of errors caused by the difference between the actual point and the line that we use to predict that point, or we add up all of those squared errors. So if I was to calculate the sum of squared error for the first problem, I would have SSE equals 1 squared plus -2 squared plus 1 squared, right? Because I'm just adding up the amount of squared errors in each of those points. So in this case, I have 1 plus 4 plus 1. So we have sum of squared error being 6. Now if we look at the other graph, notice that our errors actually end up being a little bit larger here. So for this graph, we have the sum of squared error is 2 squared plus -2 squared plus 0 squared, which means we get 4 plus 4, which is 8. And the idea is we want to have the smallest amount of error possible, because again, we want the line that best fits these data points. Since this is smaller than 8, that means that we have a better line of fit than the other one. Now, of course, the formula for getting the equation of the line is a little bit complicated. Basically, by using the specific formulas for the slope and the y-intercept, it will always satisfy the least squares criterion. Now, I want to briefly go over what r squared actually is. And to do that, I need to talk about some of the other sums of squares that are necessary in order to calculate it. There are actually three different types of sums of squares used in talking about regression. So we have SSR, SSE, and SST. SSR is the sums of squares of regression, and this is where we take the point at the line and subtract it by the mean of all the sample y values. So in other words, if we kind of look at one example of subtracting y bar minus y hat, if we take this blue line, which is y bar, and we subtract this distance here, this distance is what's used to get y hat minus y bar. When you do that between all three of these points. So we look at where each of those points are at, and we use their x value to figure out the distance between the gold line and the blue line. Now we of course already found the sum of squared error, that's represented by the distance here in black. So the sum of squares total is the difference between the point and y bar. So in fact, it is this entire distance here. Now, as you can kind of see, if we take the black distance and add it with the blue distance, we get the same thing as this distance for the red line. And so what we basically get from that result is that SSR plus SSE equals SST. So where does r squared fit into all of this? Well, r squared is just the sum of squares regression divided by sum of squares total. So the idea is we want sum of squares r to be large relative to the sum of squares total. Another way of kind of thinking about this is that if we're trying to think of our variation, well, we can think of the variation as being either explained or not explained. The variation is explained if it comes from the SSR, or the sum of squares from the regression, and it's unexplained if it comes from SSE. Obviously, we want to be able to explain how our data points are varying from one another. Or in other words, we want to be able to predict what those data values could be. So the idea is we want SSR to be as large as it can be relative to SSE. So that's in general why we want r squared to be closer to 1 than we do to 0, because we want SSR to be bigger on the numerator. Now, in case that did not make any sense whatsoever and I completely butchered that explanation, I would definitely recommend checking out 365datascience.com/r-squared/. This website actually does a really good job of explaining where r squared comes from, and it does a decent explanation of how it's used. But enough about me rambling about r squared. Let's go back and look at how we calculate the regression line that best fits our data set. Now, these are the steps on how you do this on the calculator, and of course this does require a lot of steps. However, we are going to be using Excel. So I have all this already set up for us, so let's just go ahead and dive into a problem. And I guess right before we look at a problem, we need to briefly go over the fact that we need to check our assumptions. So we need to make sure that the regression line does fit our points decently well and no outliers are present. We need to make sure that there is in fact a linear correlation. So it would be wise to do a hypothesis test or to at least compare R with your R crit value from the table. You want to make sure that your prediction is not too far away from your data set. And we, of course, need to make sure that our data points, our x, y coordinates, are simple random samples. If all these conditions are met, then we can go ahead and make our regression equation and use that to predict our y values. However, if our linear regression equation does not work, at least for this class, our only other best guess for how to predict y is to just use the sample mean y. Now, of course, in other statistics classes, or there are other statistics that you can use to try and predict the y values if it's not a linear regression. Sometimes it may require multiple variables, or it may just, in fact, require an entirely different function in general. Like it could be a parabola, for example, or a logarithmic equation that you need. So now let's look at calculating the linear regression equation for this example that we've looked at before. Last time we did look at, I believe, the hypothesis test and did find that this does in fact have a linear correlation. Looking at our values, and if our equation is y equals a plus bx, our a is our y-intercept and our b is our slope. So this gives us the line y hat equals, so it's 27.63 plus 0.05x. So if I was to predict the temperature if the number of chirps in 1 minute is 1,000, I would simply have x as 1,000, then I'd calculate what y hat is. So 27.63 plus 0.05 times 1,000. And we get our temperature of 77.63 degrees Fahrenheit. Now again, keep in mind that we already did the hypothesis test, and we know that there is a correlation. So now, what is the predicted temperature for 3,000 chirps? Well, again, we would set x equal to 3,000, and we'd solve for y hat. And what do you know? It would be 177.63 degrees Fahrenheit. Now, I'm hoping you guys are panicking because this little critter is probably not going to live very much longer if he's still chirping. Obviously, this is very unlikely to happen. I would say this is probably a little too warm. And this is why you definitely do not want to predict anything outside of your data set. So if we kind of look at the smallest and largest x values that we have here, for example, the largest we have is 1200, and the smallest, at least from what I can tell, is 864. So we don't want to go too far out of that range for a number of reasons. One, because it's very unrealistic for a cricket to be chirping 3,000 times, let alone being able to survive 177.63 degrees Fahrenheit. And two, because outside of that range, the best line of fit may not actually be linear outside of that range. It might, for example, level off, or it could change into something else, or it could just be unpredictable. So in our last example, we're looking at the ages of the best actress and best actor, and we're basically looking to see if there is a correlation between the two for each of these years for these awards here. Now, we don't know anything about this data set, so what I'm going to do is I'm going to go ahead and type both of these lists into the X and Y list. So we're going to call the actress's age X and the actress age Y. Looking at our data set, we can kind of see that points don't necessarily follow a very good line. Another thing that at least is concerning to me, and the more you're experienced with this, the more you'll see this too, this line should not have a slope close to 0, meaning we do not want this regression line to be close to a horizontal line. The closer it is to a horizontal line, the less useful it ends up being. But what we really need is to look at the p-value and our r value. R is not quite that close to -1. It's in fact fairly close to 0, or relatively close to 0. And our p-value is quite a bit larger than any of our usual significance levels. So if we were to run a hypothesis test on this, we would basically say that it appears that there is little to no correlation. So if there's little to no correlation, well, what does that mean? Well, that basically means we do not want to use the regression equation that Excel basically gave us. What we'd actually want to do instead is to just use y bar. Well, what is y bar? Well, that's a very good question. So what is y bar? Well, we just need to find the average of these. So I paste those into a list. I have equals average. Oops. Let me see if I can zoom in so you can see what I'm actually typing here. So I'm going to type in equals average. And I'm going to select all of those points. And that is my y bar. So about 45.2. So notice that because there is no correlation, we don't actually care how old the best actress is, because that doesn't actually help us predict the best actor's age. So our best guess is 45, which, as you could probably guess, it's not a very good estimate for predicting the actual age of 54 years. Well, thank you for watching.